Okay, it's really nice to be here in Texas for the first time. Remember that the communication started even before the COVID. But then it has been a few years since I finally make it here. And I was glad to find that Texas is greener than I thought. And not everybody's wearing a gun on the street. And albeit that this morning I got this Amber Alert. So that's more or less satisfied my curiosity. Today here, I would like to share with you some of our recent work on a strong electron-phonon coupling in magic-angle twisted bilayer graphene. I'm Yulin from Oxford University. I think in this audience, there's no need for me to introduce the magic-angle twisted bilayer graphene, so I will simply skip it. So we have been trying to do, well, actually, we're a newcomer into the field. We have been wanting to do this system for a long time, but wasn't successful until recently. And for the reason I'm going to cover. The first challenge is that the samples are too small for the regular RPS studies. You remember that typically our beam spot is about a few tens of micron to even a millimeter size. So then obviously what we measure is not the signal from the sample, rather it's from the substrate and other things. So until we can focus the beam spot down to the size smaller than the device, then we cannot do it. Which finally happened in the past few years, and we were able to focus the X-ray beam from the synchrotron radiation source and down to sub-micrometer. So we just dub it as a nano RPS, and in fact, micro RPS is more appropriate. So we can focus the beam using different methods, using the mirrors, using the zone plate, or using the capillary the mirror. So I will not go into the details, but with this technique, we can then scan the sample and then find the interesting regime we want to study. But there comes a second challenge, is that when we survey this device we want to study, and we found that that all these devices are typically capped, and then they want to have a bottom gate and also a top gate to tune the carrier density, and which is a bad news for us, because for the photon emission spectroscopy, we shine the light onto the sample, and then we need the electron to come out so that we can collect them and analyze the energy and momentum. So, and this geometry doesn't work for us, unfortunately. So what we need is that we can still keep the back gate, but we have to get rid of the top gate, and so that the light can get access to the sample and the electron can get out. So after the hard work of the whole community for the past maybe 10 years, and now we were able to finally achieve this goal. So before I get into the topics, and we have done a lot of preparation. Even way before this magic-angle twisted bilayer graphene, we started to study the graphene as well. For example, use this method, we were able to discover there's an in-plane graphene p-n junction. You can see that there's the different contract that actually show the p and n type regime. Long way short, and then in the end, this is what we observed. In this black regime, we saw that the graphene layer is p-n-type doped, and the Fermi level is about 650 millimeter above, and then the p region is 350 below. So the chemical potential difference can be up to 1 eV. So this was one of the early work, and also we were able to see that there's a twisted bilayer graphene, a bit not magic angle. So as this is as grown graphene, they grow different layers. Then we were able to see that the photoelectron can go through 1 layer, 2 layer, and 3 layer graphene. At the same time, we see that the graphene on this metal substrate were electron doped. Yeah, this was the early work, and so because we put this onto the metal substrate, we were not able to gate it, and but we were able to look through and find the region of interest and study that. And both this work were in collaboration with Yulin Chen, who was at Stanford back then, and now is in Peking University. Now, besides the graphene, then we also try to work on the TMD materials. And this was early work. We collaborate with Hong Tao Yuan and Xiaodong here. And you can see that we were able to image, this is the photo emission, the intensity map, that we can see that then you see this flake clearly, and this flake shape and correspond to the optical microscope scale, the image. So we were able to identify the position where we have 1 layer, 2 layer, or 3, even multiple layer regimes. Then we were able to focus the beam to the different layers, and we'll see that for the 1 layer, then the valence band top would reside at a K point, and once it becomes 2 layers, and then that valence top shift to the gamma point, then would therefore cause the direct band gap to indirect band gap transition. But the 2 layer and multiple layer, they don't really have a qualitative difference, only quantitative difference. More recently, we also collaborate with Ning Wan's group in Hong Kong University of Science and Technology, and where we studied the tungsten diselenide, because then there was in the transport that shows some very possible zero resistance states. So, and then this is a twisted bilayer tungsten diselenide, and we were able to see the Moire band a bit very weak at the gamma point, but we were not able to resolve in the K point. And so for this device geometry, we were able to study the RPES as well as STM, that these two techniques in this kind of study, they are compatible. So this provides a stepstone for us to study the match angle twisted bilayer graphene. So in addition to solving the top gate problem, then we also have some issue with the substrate. Although then for the flatness, then the magic angle TBG, MATBG usually sit on the HBN substrate. Is this substrate is supposed to be insulating, and does it really do anything to do with the intrinsic electronic structure in the MATBG? Right? If we just take a quick look, then you see that with a different twist angle between an HBN and an MATBG, you see that the moire can also change. This 6 point was the original moire from the MATBG, but then you can see that when the MATBG has different twisting angle with respect to HBN, the HBN can also, and the moire can also change the whole landscape a lot, from a high frequency modulation to a very low frequency modulation, with a period almost identical to MATBG. But then in the spectroscopy measurement, and the STM actually also found there are clear difference between the MATBG on HBN with the different alignments. For example, like this, superconductivity was only observed in the HBN unaligned MATBG. Unaligned means there's a very small angle, and in the previous the slide, you can see that the modulation from the HBN is very high frequency. The period is much smaller than MATBG intrinsic moire pattern. And here, but then what about this HBN aligned MATBG? Is that very not interesting? The answer is not. In this state, in this HBN aligned MATBG, then they discovered this insulating state where they host a corner anomaly effect. This is also very interesting. So therefore, we would like to study both samples with angle result photo emission spectroscopy. And the measurement I'm going to present were done in the ALS beamline 7, and there's the SSRF, which is a Shanghai synchrotron radiation facility with our nano RPS beamline. And you can see in this inset that how, this place turned into an end station from nothing. So it took us 5 years to do that, but finally it's done. So first of all, then we went to study this HBN unaligned sample, which is superconducting. And we can see that that's what it should like. And this is the STM map from the Elias Danis group. And you can see that even this high frequency modulation can be seen in this STM map. So So and then on the HBM aligned sample, you can see that then the spectra, STS spectra mapping look very different from the STM map on the unaligned sample, and which also agree with this simple simulation that we have. And here are the geometry of the two samples. Although you probably cannot see this MATBG on top of this HBM very clearly because it has a very low optical contrast. But for RPES, on the other hand, we have a good news because RPES we can detect we can see clearly the difference between a conductor and insulator. So here is the RPES spectral intensity. We can clearly see the MATBG region, and while the HBM is clear in the optical microscope, then it doesn't contribute to any the electron density at the Fermi level. So we were able to identify the MATBG region, and the same thing happens to HBM aligned sample. We were able to identify it, and then therefore we can choose specific spot on the MATBG to study its band structure. Here is the cartoon of this the brilliant zone. That's the top layer and the bottom layer, and we will focus our measurement at the K point or the K point or the K prime point. And here, if we zoom in, and there should be the Moray brilliant zone, or we call the small brilliant zone. And here are the overall band structure. You can see that there are two K points. See here the two sets of the bare linear dispersion. So well, this is the quick the map. So then it doesn't the data doesn't look so nice, and we can of course zoom in to study the dispersion at this Moray brilliant zone, the K point vicinity, and then to get a higher and better high resolution and better statistical data. And here are the results, and then here are the cut. The cut means that the measurement of the dispersion along different directions, and we sample there's three directions cutting along from left to right, and then three from bottom to up. And then so we want to sample it from different angle at different location so that we don't miss anything. But if we look at this, the cuts, the dispersion cut, then although they have different the dispersion details, the velocity, etc., because they were cutting along different directions and positions. But there's one common feature we can see here is this: there's a few parallel bands in all these cuts, right? And now that we can see that in the raw data, we use the second derivative to enhance this effect, and you can clearly see that there are three sets of flat bands, and then the top one is the intrinsic flat band, and the lower two, then as we will talk about later, are the replicas from the intrinsic flat band. Yeah, if you still want to analyze it carefully, then we can integrate this intensity and over the momentum space, and then we do this density plot. You can clearly see there are three kinks here, and by using the technique we learned from the transport community, for example, like quantum the oscillation, we substrate this smooth background, which effectively similar to the second derivative, and you can see there are three oscillations here, and then the amplitude just decrease. And this is a not so good cartoon to show that there's a flat band and there are replicas at a higher binding energy. So if we go to the HBM aligned sample, on the other hand, we were still able to see that the bare band, several of them. And then if we do the same thing, then we cut it through a different angle at a different location, and you can see that the dispersion now look quite different. And there are still some high intensity part other than the flat band, but you can see that this the intensity variation is caused by the band hybridization, and because they come from different band, they don't have this universal energy scale like we saw here. They were all mostly parallel, and here you can see, okay, yes, a Van Hoff singularity here and there, but you don't have the universal energy scale. That's the difference, and you can see that they look very different from the unaligned sample. And then this is a clear the one-to-one comparison then the difference, I think, is self-evident. So what's the origin of this band replicas? Then if we have the main band, now what we saw is that as a first replica, then the energy get to dissipate by something, then it could be some sort of boson. And then if this interaction is strong enough, then you have a second replica or even higher order replicas. So, and then we see that at the beginning with this, the replicas right underneath the original flat band. We thought this the boson should reside at a gamma, around the gamma, because there's no the momentum transfer. And yeah, this is quite similar to other systems and 2D systems like the iron selenium on the strontium titanate, the substrate, or there's a 2DAC, the strontium titanate system. So that's motivated us that this probably could caused by some sort of boson, but what boson, right? And yeah, to figure out those boson, then we did some more analysis and found that this replica and the flat band, they are evenly spaced, and the energy separation is around 150 millieV. This is pretty high. And well, this is the energy uncertainty in the nano-RPS measurement. And well, this is the phonon spectrum, but before we got to this point, we thought about that. Could it caused by this the plasmon? But then, according to the sample is a very, very weakly doped, so then the Fermi surface is very small. The plasmon's frequency cannot be as high as 150 millieV. And whether can it be? It can be the electronic origin, because then it's also unlikely, because for example, like Landau level or other electronic correlation will not give you this evenly spaced the energy spaced the replica band. The spacing, energy spacing will vary. So then we landed on to the phonon, and then there was no magnon to consider here, right? And the phonon we got out of this phonon spectra, but to our very disappointment, at the gamma point there's no phonon mode coincide with this 150 millieV. Although the energy resolution is not so great, but it shouldn't be so large to miss it. So here, right, then there's nothing here. But then later on, we realized that in this the MATBG system, this kind of zero energy momentum transfer doesn't necessarily need a gamma phonon. A K phonon can also do. So, and then if we went to the K point, the vicinity, and indeed there are actually 3 phonon bands go across it. And then although we like this TO phonon, it's kind of flat, but we don't know yet. So so we collaborate with the Shida's group, and he did some calculation, and his result calculation really indeed turned out that show that this red the phonon branches interlayer and transverse optical phonon indeed have a higher electron-phonon coupling strengths. That's agree with our intuition that this flat band has higher density. And so how are this replica happens? And then we can see there are flat band from K and K prime point, and if you turn on this is a K phonon electron-phonon interaction, you can see this K flat band after scattered with this phonon, and then go to the K point as a first replica, and then will scatter back. And similar things happen from the K prime to K, and then go back to K prime. So also then, if we now we have this phonon hypothesis, then we went to do the more calculation. So we actually asked the Yao Wan's group, that is we found his paper in the previous STO2 deck, and then he worked on the replica, and then we asked him to do something similar in this system, and indeed his calculation show that for the different filling, half filling and quarter filling, and if we turn on this electron phonon the interaction coupling, and you can see this the replica at the separated by the phonon energy. Okay, so far. So we've discovered the flat band replica found in an unaligned superconducting MATBG and HBN. No flat band replicas observed in aligned non-superconducting MATBG and HBN. So replica attribute to the inter-valley electron-phonon coupling. But there are still two questions that people naturally raise, right? How repeatable are these replicas? And the second one is what's the correlation between EPC and the superconductivity? We want to address both questions. So the first one is that by this, for us, right, the newcomers, to make this device is really difficult, and maybe unlike this expert here. So after half a year's effort, we were able to fabricate and also measure and found this HBN unaligned inmagic-angle device number 2. Actually, in the past weekend, we just got device number 3, even with better results, and we were able to see this replica again in the new devices. And you can see the different cuts, and then they show there. And what about the non-superconducting sample? And then for the non-superconducting sample, other than this misaligned aligned with this HBN, and this is to address, the previous one is to address the repeatability of this flat bands replica. And this is to try to study the correlation with superconductivity. So now in this way, we kill the superconductivity in a different methods, right? It's not aligned with the HBN, but just change the twisting angle. And although you can see there are still flat band here, you don't see this replica anymore. And there are, if we just crank up this twisting angle, we don't see the replica either. So you can screw up the superconductivity either by aligning it with the substrate, or you change the twisting angle. And if the superconductivity doesn't show up, then we don't see the replica. So that means this replica occurrence and the superconductivity has a pretty strong correlation. So this is the update summary. So TBG, and we make it MATBG, and then unaligned superconductivity and replica observed. If it's aligned, no superconductivity, the replica not observed. And then if we have non-magic angle TBG, then either smaller and bigger angle, then the replica not observed. So here is the updated summary, and then we now can address the last two questions. Replicas are repeatable, and the correlation with the replica and superconductivity is strong. Okay, so I see the chair is right there, so I would like to acknowledge my collaborators, and this is the Chen is the postdoc actually led the effort, and then the sample was from Ali's group, and the theory was supported by Andre, Yawan, and Chaoxin and Xidai. And here are the synchrotron folks that we really owe our appreciation. Thanks to. Okay, that's it. Thank you.
Thank you very much. Questions there?
Hi, thank you for your talk. I have a question. So if you have inter-valley coupling by phonon or anything, is it possible to see the like Kekuli distortion of the graphene lattice? And why is it
distortion of the graphene lattice?
Yeah, this is Kekuli distortion, like √3 by √3 enlarged unit cell.
So
and
I think it's possible, but then for our technique, we are not able to see that. Probably then we need to use STM or other local probe. Right?
And why is it absent in the aligned case?
What is absent in the aligned case?
The aligned with HBN.
The replicas, right?
Why is
the electron-phonon coupling?
Why is the phonon? Yes.
Oh, I will not say that it disappear, right? The electron-phonon can't disappear for the unaligned case, but it will be significantly, at least significantly reduced to the point that we don't see the replica. And there could be, so currently our understanding is that there are, this is the one of intuitive picture. And you can see that according to our calculation, this, you can see the HBN unaligned sample, the density of the electron is focused on, accumulate at the AA site from STM. And for the aligned one, it's much more distributed. And for this ITO phonon, actually, the distortion happens right at the AA point. So this is quite natural. that for this case, then the electron-phonon coupling is stronger than this one. Of course, now, if you want to study from the model point of view, and for the unaligned sample, then because the HBN interaction with the MATBG is weak at a pretty high frequency, and it's more like this a freestanding MATBG. So the K and K prime point is pretty much degenerate in the energy, right? And after that, the wave function. But then if you have the HBN aligned, then this with this the HBN moire, which can be seen clearly here, it's very strong. So that the K and K prime degeneracy now is lifted. So if you want to scatter from K to K prime, then the cross section is much less. I think, yeah, these are our current understanding.
Okay, one more question.
Yeah, I have a question to the population, thermal population of your phonon mode. It's very high energy and you are at low temperature. So how can you explain that you see an effect at 10 Kelvin while your energy of the phonon mode is 1200 Kelvin? So yeah. How does that?
So yeah, that is a very good question. I didn't show the temperature there. That's actually measured at room temperature. That's partially the reason why the spectra is not as sharp as you saw. And there are actually two reasons.
Temperature dependence then? I mean,
yeah, actually, yes. So so for this one, and there are two reasons for us to measure it at high temperature. One is that what you're talking about, right? And the second one is for this sample, as I talked to a lot of people in the community, is that we always observe that when MATBG on a HBN sample we will measure is that the flat band is very have very low density of state. It seems that it's weakly p-doped. So if we have measured this sample at a very low temperature, actually I have some result and I can show it to you. Do I have the comparison between high temperature and low temperature? So basically at a low temperature, then this flat band is depopulated. So we were not able to see the replica. So that we need to increase the temperature to populate it, thermally populate it. And then because we cannot put on the top gate, and then you can ask why we don't put on you use the back gate to gate it. Yes, we tried. So this if the HBN is too thick, and you cannot gate it effectively, too thin, and if the HBN the quality is not so good, and with the X-ray shine on the sample, it causes a leak, and so we cannot gate it very effectively. So then, in the end, we found this thermal population was the way we went. Yeah. So, but more recently we have been trying to gate it. We continue our effort and then got some result there, and it's quite interesting. We saw that actually. Yeah, let me show it here. We saw that there were upon gating, this replica intensity actually doesn't change monotonically. This is another proof that this intensity is not caused by the band hybridization. If you cause band by the band hybridization, it doesn't really matter what feeling, right, you have. But I think this is an indication to show that this is really caused by this flat band, and the electron correlation does play a role in here. So this is the data. We just got it on Monday.
Okay. Thank you. Well, we have to cut. So the next speaker could go and put the slides on. Let me take an opportunity to ask something. So obviously now this electron-phonon coupling really depends a lot in the orientation of this HP2 layer. So do you think that the values where you see the replicas of the electron-phonon coupling is the maximal, or could you still increase it by some other configuration?
That's a very good question. So we actually, this is the next things in the pipeline we want to do, right? So, but that really depends on how we understand the underlying mechanism. We have these two understanding I just briefly discussed, and then if we along this understanding, then we want to try to increase the density at the AA site, for example, with different methods, and so that then possibly we can enhance the electron-phonon coupling and therefore enhance the superconductivity temperature, superconducting temperature. This is something we are doing now.